how does it play into molar volume? STP, the conditions of STP controls the constant of molar volume. It's only true at STP. So it's very helpful to assume STP and go with a constant 22.4 liters per mole. Yeah. 6. Why do we use SI units of moles? Anybody? Why do we use SI units, period? Yeah.
So there's no miscommunication.
Right, and so across the board, across the international, SI means system of international units, across the entire world, we're all using the same units, so we all can repeat each other's experiments. That's a big part of science and being able to reproduce our experimental results. Hopefully, pass up reading guide 12 in a second now, and then let's go through this warm-up together. That sheet of, we are going to use the back side of this today. It's got a little flow chart on it. We're going to use this today. Okay, so find yours. Find yours. Huh? I think I do. That was good. I'll see if not Who does not have one? Huh?
Yeah. Wait, no, I do.
Yeah, I gave this to you guys a week ago. Okay, reading guides up here. Thank you, thank you. Thank you. Thank you. Yes.
I'll go on one.
Oh, hold up. I'll give it to you a little bit. Okay, yeah, more. Alright, so I have a couple house cleaning things we need to do today. I have some progress reports for you because you have spring break soon, right? And then right after that, we have a lab the day we get back, then we have review day, then we have quest part 2. Okay? So I'll make sure we had a review day before that. Because there's no way in Hades we're going to get all this stuff done by tomorrow. Okay, we're a couple days behind from the SNP. So I have your progress report so that you can look at your missing assignments and make that stuff up on your own time because let's see, April the 9th is when our grades are due. That's that Thursday after your quest. So I'm getting your quest graded, and that's going to complete that other half of your test grade that I said the quest was worth. It's for each of it's a half test grade. So I'll give that out to you as we go. And I graded like a boss last night, so you guys have a lot of stuff to talk about. Okay, so BC, what does that stand for? Balanced chemical equation, because who wants to say balanced chemical equation when you can say BCE, right? So, what do the coefficients mean? Generically, what do coefficients mean? Huh? Okay. So it's like a ratio of things that you need, right? So if you're baking a cake, you get 1 cake box, you get 2 eggs, you get a cup of oil, and you get as many sprinkles as you can find, right? Do whatever you gotta do. But the ratio is 1 cake box, 2 eggs, and so forth. The coefficients are simply ratios of reactants and products. That's all it is. So if we balance the chemical equation appropriately, we know the ratios in which they are created or made. So for every 1 cake box, you're going to make 1 cake. For every 2 eggs in that recipe, you're going to make 1 cake. For every, whatever I said, cup of oil, you're going to make 1 cake. It's just a ratio. So we also need to do a little bit of review. I typed up, you guys gave me some really good feedback on the soccer tip thing yesterday, so I could figure out what we're still struggling with, so I typed up a 4-page document of review. And I'll share that with you in a little bit. Okay, so conversion between moles and particles. What are the 3 particles? 4 millunits, atoms, and molecules, right? And we have to use these in the right way. 4 millunits are ionic, atoms are elemental, right? Elements and molecules correlate with what kind of bonds, right? Covalent bonds, right? Okay, the conversion between mass and moles is called mass and moles. What comes to mind? Molar mass, right? If you're going between mass and moles, that means you're using the molar mass. Where do you find the molar mass? You add it up from the elements on the periodic table. So if you're going from mass to moles, you'll have some number of grams given, then you're going to multiply by 1 mole. It's always correlated to 1 mole, right? 1 mole of X, whatever we're talking about, over its molar mass. Its molar mass is what we calculate from the periodic table. So molar mass in grams. And we do that because we have to cancel the units. So it's all about canceling units. We're going back and reviewing a little stoichiometry so we can start to apply it to bigger, better things like reactions. Okay, so one more review here. What's the conversion for molar volume? The conversion is what? 1 mole is, thank you, 22.4 liters. It's all related back to 1 mole, of course. And what are the conditions here? I know STP stands for standard temperature and pressure, but what are they? What's standard temperature? So 25 degrees Celsius. And I'm sorry, I keep saying 25. It's 0 degrees Celsius. Sorry, we have standard conditions in AP, and it's different than standard conditions. So 0 degrees Celsius in 1 atmosphere. Okay, and so those are our 3 conversions we already are like pretty good at. We just got to keep making sure we always refer to 1 mole. Now we're going to apply that to a balanced chemical equation format here. So this is what we know. We know we can take mass to moles, particles to moles, and then volume to moles, or vice versa. You can go moles to mass, moles to particles, or moles to volume. You know the conversions, those 3 that we just went over. So we're going to be using Avogadro's number a lot. We're going to be using 22.4 liters a lot, and whatever the molar mass of a particular compound is. Okay? But we're going to incorporate one new one, which is called mole ratios. It's just a coefficient over a coefficient. And that's kind of what we talked about last week, but we have a little bit more. Oh, here's my review. So I will show you guys this towards the end, but I made a bit.ly address so you guys can go on there. I pretty much recapped anything and everything people asked me to. So if you go on the bit.ly address, then it will pull up a Google Doc that I made with you guys for extra help. You don't have to review this tonight. This is just something I created so you guys could get some help if you needed it. Organic was one of the things we talked about. People have problems balancing combustion. People have problems predicting products. I made a synthesis decomp single activity series, double replacement, how to use the solubility rules, net ionics, how to do that again, example, and there's a picture there. Oh no, there it is right there. And then I put some good videos up here for links or anything that you might want some extra help with. So take care of yourself whenever you have time to. But I made that so you guys had some extra resources. I will show you the link to that again. So it's there. I'll pull it back up later. Okay, so for real, we're starting now. Stoichiometry. Stoichiometry, we already have a lot of background on. We have the compositional stoichiometry, which was like, you know, percents and grams per mole, Avogadro's number.
Please call an announcement. Students who are going with the Hosa Club, please report to the tennis court for the buses. Students who are going with the Hosa Club, please report to the tennis court at this time for the buses.
Okay, so stoichiometry, with me? Stoichiometry is just like a fancy word for chemistry math. That's all it is. But what we are going to focus on today is more of the ratio within a chemical equation. So the ratio in a BCE, okay? The mole relationship, it's called a ratio. So you don't really have to write much down here because we're going to start implementing and practicing. So when I say ratio from a balanced chemical equation, that means you have to know the coefficients. That's pretty much the key to this game now. You have to be able to balance. That's what we spent a week or so doing, predicting products, balancing chemical equations, and so forth. There's not much to write down here, so I'm moving. You just need to know mole relationships or ratios. So let's practice from this equation here. This equation here, we have multiple ways you can interpret this. So you can see that hydrogen gas reacts with oxygen gas to yield water vapor. But what's the recipe? How many hydrogens do you need? For every 1 oxygen, how many hydrogens do you need? 2, okay, because there's a ratio of 2 to 1. Well, for every 1 oxygen you have, how many water vapors are you going to make? 2. For every 1 oxygen you have, you're making 2 water vapors. It's just a recipe, but now we're using it a little bit more explicitly. There's different ways you can interpret this, though. You can call, because everything's related back to Avogadro's number, everything. So technically, you can divide all these things by Avogadro's number to get a specific ratio. So 2 molecules of hydrogen plus 1 molecule of oxygen yields 2 molecules of water. I like that rate. It's pretty much you can do what you want with it. based on the fact that you know the coefficients. So you can call these 2 molecules, 2 moles, 1 mole, 2 moles, or since we can assume STP unless told otherwise, we could even say, oh, this 2 could be 2 liters, because these are gases, right? 2 liters, this could be 1 liter, and this could be 2 liters. So the ratio is flexible in its unit. Depends on what you need in the problem. We commonly will be using the mole ratio versus like the liter ratio. It's just a coefficient kind of game now, okay? So, from this equation, the mole ratios we were using the mole unit would be 2 moles of hydrogen is equivalent to 1 mole of oxygen. It's very specific to this reaction though. So this is called a mole ratio. And you can write the mole ratio as a fraction like we've done everything else for stoichiometry for conversion factors. 2 moles of hydrogen is equivalent to 1 mole of oxygen. So that is my mole ratio. Or I could have done the other way. I could have done 1 mole of oxygen over 2 moles of hydrogen. But no, I have to write the identity of what the heck I'm talking about, because now we're playing with multiple players in the game. So you gotta make sure you're actually writing down what you're talking about, the identity. But this is a really, really useful way to get from, you know, apples to oranges, from one reactant to another product, without doing like 15 steps to stoichiometry. You can do 1 step, and it can get you from one totally new thing to another. So we'll practice looking at BCEs and getting the mole ratios. But this is the easy part today, okay? This is the easy part. We're going to start practicing and applying this in a minute. You hopefully are not writing every single thing on this slide, because it's kind of a recap, and then this is the new stuff. Okay, I'll give you one more second. Okay, so from this equation, 3 calciums plus 2 3 iron-free permanganates yields 2 calcium permanganates and 2 irons. What is the mole ratio between calcium and iron? What's the mole ratio between calcium and iron? 3 to 2, right? You're just saying from calcium to iron, the ratio is what the coefficients are. 3 moles of calcium equal, and this is just saying for this recipe, these are considered equivalent to one another, 2 moles of iron. So you could then write that a little bit more like a conversion factor. 3 moles of calcium over 2 moles of iron. So it's just literally taking the coefficient and applying it to a fraction. So what's the mole ratio between iron-free permanganate and iron? Iron-free permanganate and iron. 2 to 2, right? So from iron-free permanganate to iron, it's a 2 to 2 ratio. 2 moles of iron-free permanganate over 2 moles of iron. So notice I'm writing moles, because they're mole ratios. Thumbs up if you get this. Yeah. You can simplify it, but I wouldn't waste my time because it's probably going to be just use it as like in a calculator calculation anyway. So just write it like that because it's straight from BCE. You don't have to waste your time reducing down. All right, so tell me the ratio between calcium, permanganate, and iron. Calcium, permanganate, and iron. 3 to 2. So you can compare anything. You can compare reactants to products, products to reactants, reactants to reactants, products to products, apples to oranges. You can compare anything as long as you have the coefficients. That is the beauty of having mole ratios. So I think we get this. Let's see if we can apply some of it. Okay, let me do one more. For this one, what's the ratio between oxygen and hydrogen peroxide? 1 to 2, right? Oxygen has a 1, hydrogen peroxide has a 2, so it's a 1 to 2 ratio, but you have to write moles of apples, you know, oxygen in this case, over moles of other thing, hydrogen peroxide. You've got to identify it, because if you don't, you won't know what the heck you're talking about when you start canceling out ratios and stuff like that. Right, thumbs up when you're good here. This means I understand mole ratios. Yay. Okay. Okay. I'm feeling good about life here. Okay, so what we're gonna then now kind of combine together is our old knowledge and our new knowledge, and this is a baby scale. Okay, I'm gonna show you the big scale in a second. You're gonna take your mass of mass of apples, go to moles of apples, so whatever reactant you want. You can get between moles of apples and moles of oranges now because you know the mole ratio from the BCE. Okay, and this is bigger and better on your page. I'll show you your flow map in a second. But this means that you can get from mass of like oxygen to mass of hydrogen by going through this little conversion of mole ratios back to molar mass. So we're going to do a lot of practicing back and forth converting from California to North Carolina. Okay, we're going to be converting from one side of the equation to the other. You can convert from mass or from atoms or from liters or from multiple other things. This is the one you have in your paper. You find it? Okay, so I'm just going to tell you to fill in the blanks on a couple of these because I did leave you some blanks, I think. The first thing I'm going to hone in on is the fact, right smack in the middle, you have moles of X to moles of Y. You have to use the mole ratio system from the BCE. So mole ratio from the coefficients. Kind of what we just talked about. That's how you're going to get from one thing to a whole nother thing. But before you get to this point where you convert from moles of apples to moles of oranges, you probably are not going to be given moles. You're probably going to be given grams or liters or some other unit, atoms, formula units. So at the top of this chart, you've got anything I could give you under the sun, right? I could give you particles, volume, mass, and you know how to convert to moles from those. This new one is molarity. Molarity is like chemistry concentrations, right? So Kool-Aid. You make Kool-Aid, you put like 2 packets of stuff in it and a liter of water. Okay? It's concentrated Kool-Aid. Really, really, really concentrated Kool-Aid is like syrup. And then really, really dilute Kool-Aid is like water, right? So it's the same thing for chemicals. Really, really strong concentrations have a high molarity. So if I want you to tell me, if I tell you I have 2.0 molar M, big M right here, means molar. Molar means concentration. Okay, so I'm giving you a little bit of extra information here. 2 molar of something means you have 2.0 moles per 1 liter of solution. Moles of X is what I'll say, since I'm on the X side of things. So this is one extra piece of information I could give you. This is extremely useful because isn't it a conversion factor? It's a fraction, right? It's a conversion factor. So if I tell you 2.0 big M, break that down into the 2 components, moles per liter. Then what you can do, and I'm going to kind of just keep writing over here, you can actually get to moles from that. And so obviously because I'm showing you can get to moles, and you're like, well, how do I get to moles? Well, let's say I gave you 2 liters of solution. You can do this part in your head. If I give you 2 liters of solution and I tell you the molarity, the concentration is 2 molar, that means there's 2 moles per 1 liter. Hey, I got 2 liters. How many moles do I have? 4. Okay, I'm going to show you the dimensional analysis way. 2 liters times molarity, pop this little fraction right here, 2 moles of X per 1 liter, what cancels? Liters and liters, right? So 2 times 2 is 4. You just did that in your head though, but I can show you it from a mathematical standpoint as well. So this is 4 moles of X. So you can take anything I give you, you can get to moles of X. Then you can take your balanced chemical equation and convert to moles of your other substance, and then on down you can convert back to grams or atoms or whatever. You guys are a plethora of knowledge right now, okay? You've got so many conversion factors you could use. So let's practice. This is our first example. You have it? Did I copy this for you? Yeah? I'm doing 3 examples, A through D, or A through E each. You need to write down all of them with me because you're going to have your own 3 to do afterwards. Okay? So, first of all, for every single thing, we need to write down the BCE and our givens. So, balanced chemical equation. Consider the synthesis. Synthesis means what? Generally, what does that reaction look like? 2 things go to 1 thing, right? So the synthesis of aluminum oxide from its elements. So what are we synthesizing? What are we making? Aluminum oxide, so that's our product, yeah? Aluminum oxide, how do I write aluminum oxide? Al2O3, good, because you're crisscrossing your charges. Okay, so from its elements, what are its elements? Aluminum and oxygen. Aluminum and oxygen. Is that how you write oxygen? No, your diatomics, right. Gotta make sure you have your diatomics. Okay, balance. So I'll put a 2 here and a 4 here. Okay, so I had 3 oxygen, so I needed 3 here. That made 6, so I had 6. And you're like, oh no, now I got 4 aluminums, pop a 4 there. All right, this BC should take like 10 seconds. We should be pretty proficient. Okay, so now we've got our balanced chemical equation. Let's write down our givens. What are the mole ratios? Oh, this is just a mole ratio problem. Okay, this one's really easy. What are the mole ratios that can be derived from this balanced chemical equation? And when I say mole ratios, I mean every single combination of mole ratios you can make. So, aluminum relates to oxygen, right? And aluminum relates to aluminum oxide. So 4 moles of aluminum over my first comparison, 3 moles of oxygen. Okay, so that's my first one, and I could write it either way, up and down, but I'm putting aluminum on top. My next one, 4 moles of aluminum to what? Right, 2 moles aluminum oxide. Okay, so there's 2 so far. What else can I make a comparison between? 3 moles of oxygen to the 2 moles of aluminum oxide, right? So 3 moles oxygen over 2 moles aluminum oxide. I'm pretty sure there's no other actual comparisons except you could flip all of these. You could flip them all to be, 3 moles of oxygen on top, 4 moles of aluminum on the bottom, and so forth. So the mole ratio part, writing it, is just simply pulling coefficients down and writing the units. Okay, so now here's the real problem, B. Okay, so the first one is just for help, so we can make sure we're good. How many moles of aluminum are needed? So I'm going to scroll down some. So question, moles of aluminum needed to form 2.3 moles of aluminum oxide. So that's only 2 pieces of information I have, my unknown and my known. What do I start with? I start with the known, right? I can't start with a question. I have to start with my known. So if I have given 2.3 moles of aluminum oxide and I want to get to aluminum, I want to get to moles of aluminum. I have one step. What do I do? Yes, use which ratio? The second one, good. So I'm using this one because I'm getting 2 moles of aluminum. Do I write it like that or do I flip it? Write it like that because I need moles of aluminum oxide on the bottom. So I'm going to write it exactly like this. 4 moles of aluminum over 2 moles of aluminum oxide. So across the board, you would be multiplying 2.3 times 4 divided by 2. So 2.3 times 4, hold on, I have this answer. What am I trying to do? This in my head right now. Ah, 4.6 moles of aluminum. So 2.3 times 4 divided by 2 is 4.6 moles of aluminum. Done. So not bad, right? Not bad. Huh? And, oh, sorry, good question. Somebody asked me about sig figs on the thing you did yesterday. This is a measurement. 2.3 is a measurement. It has to have sig figs. It's got 2 sig figs in this problem. These, they're not measurements really. They're ratios. Ratios are me pulling a coefficient down, plopping them in a conversion factor. So do not look at the sig figs of this because everything would be limited to 1 sig fig, right? And who wants that? We want some accuracy here. So we have 2 sig figs in our final answer. All right, next one. How many liters of oxygen? Oh, we got liters going on here, okay? Question, liters of oxygen. At STP, what pops into your head? When I say STP, what pops into your head? 0.4 liters per mole, okay? All right, so how many liters of oxygen are required to completely react with 8.4 moles of aluminum? What am I starting with? What? Or 0.84, sorry, 0.84. Starting with 0.84, good. Starting with 0.84 moles of aluminum. What do I do now? I'm not wanting aluminum, period. What do I want to get to? What identity? I want to get to oxygen, right? So I can't go directly from moles of aluminum to liters of oxygen. This one's going to be like at least a two-step process. So you want to get out of aluminum first into your desired identity, oxygen. So I need to use a mole ratio to get out of moles of aluminum into moles of oxygen. So I'm going to go all the way back up to the BCE. Moles of oxygen in aluminum, moles of oxygen in aluminum, 3 moles of oxygen for every 4 moles of aluminum. I'm just looking at the coefficients. So 3 to 4 is what that's saying. So I just said 3 moles of oxygen for every 4 moles of aluminum. I'm simply pulling out a BCE. So moles of aluminum are canceling. Great. Now I've got to get rid of moles of oxygen to liters of oxygen. What comes to mind? Right. 22.4 liters of oxygen, which is just the gas at hand, is equal to 1 mole of oxygen. So then the moles of oxygen cancel, leaving you with liters of oxygen. Yay, that's what you wanted anyway. So then in your calculator, you do 0.84 times 3 times 22.4 equals, divided by whatever 4 times 1 is, 4. Okay. So you do that in your calculator. I'm asking for you guys to practice in your calculator on your own. You want to make sure that you're good with that. You can participate in class right now. Some of you guys are falling asleep on me. Today is a mathy day. So bear with me here, okay? This is 14 liters of oxygen. 14 liters of oxygen. So you should be doing 0.84 times 3 times 22.4 equals whatever divided by 4. Or you can do 0.84 times parentheses 3/4 times 22.4. Some of us messed up on our request because we did not calculate very well. You got the math down, you got the work done, you got the units there, and you put your calculator wrong. So practice that for a minute, stand up, get a stretch break in, and then we have another example. I'm doing as many as I can so you have as much support as possible here. Okay, while you're doing that, I have a demo for you. I have a demo for you. I'm gonna do it. I'm gonna do the first one. I'm gonna do the crazy one. I gotta do my bottle one. No, I'll do this one first. I'll do the bottle one. Okay, so I need to show you something with my magic wand. My magic wand. Okay, I have a solution here. You see the solution's liquid, yeah? Liquid. Okay, watch. 3, 2, 1. What is it? You're the closest one. What is it? Touch it. It's so hot. It's an exothermic reaction. It's not our reaction, actually. It is hot. Look, 1, 2, 3. Nothing. Liquid, solid. What is liquid? Gas, solid. Pass it around. What's my magic wand? I can't tell you my secrets. I didn't. I have that in. Well, then why did it make it solid from air? Air's not magic. You can pass it around. Pass it up to the front when you're done. That's called a supersaturated solution. It is incredibly unstable. If you look at that solution the wrong way, it precipitates out. So I had to keep it back and keep it nice and cozy and, make it dinner and take it to a movie. I had to do all this stuff to make sure it did not precipitate out. Because if you look at it wrong, it's like, nope, not staying liquid anymore. I will precipitate. So I just kind of tapped that, made it too ferocious up in the class. And I have jokes for you between because I know today's going to be a great day. Okay? Heavy metals! Long live heavy metals! Miss Inlet, you're hilarious. Thanks, guys. You're awesome, too. Okay, so let's go ahead and do the next reaction. Pass around the exothermic reaction as you go, okay? Okay, so we're going faster this time because you got the hang of this. So let's go. Combustion of propane gas. And you go, oh, what's propane? Remember, your organic stuff. Meth, F. What's next? Prop. What's next? Bute. Bute. What's next? Pent. Next. 1, 2, 3, 4, 5, 6. Hex. 7. Pept. 8. Oct. Okay, so pretty much if it says any of those ane, then you're doing 2n plus 2 to get the number of H's. These are telling you the number of carbons. Okay, so propane, how many carbons? 3. 3 carbons. How many H's? 8. So C3H8. Combustion means reacts with oxygen. Makes what? Carbon dioxide and water. Balance this baby. How many carbons do I need? 3 carbons. How many hydrogens do I need? How many waters do I need? I need a 4 in front of the water because I have 8 total. Total, how many oxygens on the product side? 6 plus 4. Yeah, you see there's 6. So 3 times 2 is 6 oxygens plus the 4 times 1. So that's 10 oxygens. All right, I can do 10 over here. How do I do that? 5. And there's a 1 up here. Okay, so I'm making my coefficients in different colors so they stand out to you as mole ratios. Okay, question. How many grams of oxygen? You should be writing these down with me because if you ask me questions later and I go, where's your examples? And you go, I don't know, then I'm going to walk away. All right, so how many grams of oxygen, oxygen gas, by the way, because it says oxygen, but it means oxygen gas, are required to burn, aka combust, 13 grams of propane. So, what am I starting with? I got one thing to start with, right? 13 grams of propane. Okay, I can't do crap with grams, people. What do I have to do? Where's the moles? So what do I need from that? You need what? You need your periodic table on your desk? So you said? Periodic table on your desk? Or look to the side? Or that side? No, you can't see numbers. I can't see numbers anymore. I want to get out of grams to moles. What do I do? Add them up. 12 times 3 is 36 plus 8, 44. 1 mole of propane. 44.09 grams of propane. Okay, I'm just making sure you're connecting your dots. You know you don't just find the number, you add it up. So your grams of propane are gone. Now we're in moles of propane. We still don't want moles of propane. Who do we want to get to? What identity? Oxygen. So I got to get out of moles of propane 2 moles of oxygen. With what ratio? Tell me moles of oxygen first. 5, and you're finding that from your BCE. Tell me moles of propane on the bottom. Just 1, because there's a 1 coefficient over here for your BCE. Good. So the mole ratios are really helpful because you get to go out of apples into oranges. Oxygen in this case, right? So now we're almost to grams of oxygen. Last step, what? Because we're going to grams of oxygen, remember? We have moles of oxygen. Huh? I don't need to. That's the step I don't want to do. I don't need to go to liters. I want to go back to grams automatically, right? So you know you want to get rid of moles, right? So I'm going to put 1 mole of oxygen on the bottom. How do I get from moles of oxygen to grams of oxygen? The molar mass. What's the molar mass of oxygen? 16. That's just 1 oxygen. I have diatomic oxygen. 32. Okay, so there's a big misconception. Anytime I say gas, you have to use the 22.4 liters. No. You only have to use 22.4 liters when you have volume involved. And nobody said anything about volume. Period. Nothing. So don't use it. So you'll notice everything cancels. Moles of oxygen cancel. The only thing left is grams of oxygen. Yay. That's what you wanted to get. The answer should be my math. Where's my math? There it is. Okay. 42 or 47.2. Anybody else get that? Yeah, thanks. Okay. Good job. Good job. Okay, so I'm going to keep scrolling back and forth up to the BCE because I got to see my BCE, but your BCE's in your paper, so you shout it out when you're ready, okay? All right, so next question. How many grams of carbon dioxide? Question. Grams of carbon dioxide are produced when 0.50 moles of propane reacts with excess oxygen. So it's just saying reacts. Like, okay, we got it. We know it's reacting with the oxygen. So, what do you want to start with? You ready? So 0.5 moles of C3H8. Okay. I don't care about propane. What do I care about? What do I care about? I don't care about oxygen. What am I looking for? Carbon dioxide. I'm looking for carbon dioxide. So get me out of propane to carbon dioxide. How? Mole ratio. I heard it. What is the mole ratio? You know you've got to have 1 mole, or thank you, it's 1 to 3. Good. So you have moles of propane on bottom because you have to cancel moles of propane. You know you want moles of carbon dioxide on top because that's the new identity that you want to get to. Then to get these numbers, you go to your BCE and go, oh, well, I have 1 propane and I have 3 carbon dioxides. So ratios, 1 propane, 3 carbon dioxides. That's simply from the BCE. And I'm still not to grams of carbon dioxide. I'm to moles of carbon dioxide. What do I do now? Molar mass. 1 mole of carbon dioxide weighs 32 plus 12. 44.01 grams of carbon dioxide. Good. To be exact, right? Okay. So everything cancels. Moles of propane, moles of propane, moles of carbon dioxide, just top and bottom, moles of carbon dioxide. The only thing left is grams of carbon dioxide, which is great because we want that anyway. So that gives us 66, it looks like 6.6, it's 66 grams of CO2. Alright, so a lot of conversions here. Last one, you guys start. You shout it out if you want to, but tell me exactly what I'm writing or what you're writing on your paper. So question, liters, like you said, liters of oxygen. Keep going. So I'm starting off with this 13.0 grams of propane. Okay. So I'm starting with that. Yeah? Okay, so I'm starting off with 13 grams of propane. Right, tell me what's next. Right, get that to moles. What was the molar mass of propane? You wrote it previously. What goes on top? 1 mole of propane goes on top because we want to get 2 moles, right? What goes on bottom? 44.09 grams of propane. Okay, so grams of propane have been canceled. I don't care about propane. What's next? How do I get to oxygen? What is the mole ratio? You have your BC in front of you, yes? So 1 mole of propane, I heard you, is how many? 5 moles of oxygen. So you're just looking at the coefficients for this on your BCE. Okay, last step. So I'm here in liters, and I'm here in the constant, right? So 1 mole of any gas, in this case it's oxygen gas, is 22.4 liters. There we go. So everything cancels. Grams of propane, moles of propane, moles of oxygen. Double check your units and everything, and you should get liters of oxygen. Maybe tell me what you got. 33. I got 33.0, but I'll go with 33.1. Whatever works for you, as long as you got 3 sig figs, works for me. Because I had 3 sig figs in my original here and everything. You know, these are ratios. They don't matter. That's a constant. So 3 sig figs wins. Okay. Ooh, I see molecules now. Molecules. All right. So tell me how to start here. So question molecules of H2O. What am I starting with? 10.0 grams of propane. Good. All right. Give me where I gotta go. I like you guys participate, so you guys are reassuring yourselves you're correct. So going to moles, right? 1 mole of propane. What was the molar mass again? 44.09 of methane. I mean, propane. Jeez. Okay. Next. 4/1. So you're telling me the mole ratio, right? Because mole ratios get you from apples to oranges. You want to get from propane to water. So 4 moles of water for every 1 mole of propane. Okay? And the reason you're doing this is because you're canceling out top and bottom. Canceling out top and bottom. So what's canceling next? You're canceling out what? Moles of water. 1 mole of water. You're canceling that out. You know that because you have to cancel from the previous numerator to the next denominator. But are we able to go directly from moles of water to molecules of water? Yeah. What number? Avogadro. 6.022 times 10 to the 23rd molecules of water. This is more accurate. For 15 years I've used this, so I was supposed to stick with, maybe not 15 years, let's go like 10 years, I'm not that old. Okay, so I've used that forever, and I constantly do that. I dream about off-by-the number. Okay, so then everything cancels except for moles of water. I'm sorry, except for molecules of water. Moles of water do cancel. So in your calculator, you would have to put 10 times fraction 1/44 times 4 times 6.022 times 10 to the 23rd. And I like to put parentheses on everything just in case it's in a denominator, because then it won't work well if you don't put parentheses. Yeah. Yeah. You mean all the numerators?
Yeah.
Yeah, you can multiply across the top all the way, equals, and then just divide by 44.09. Yeah, a lot of people like to do that, because that way you don't have to mess with the parentheses. Okay. So that gives you a number such as 5.46 times 10 to the 23rd molecules of H2O. Whew. Long one, guys. All right, I have one more that I'm going to do with you. As promised, I have a demo. Let me get my goggles on. I'm just trying to break up the monotony of me talking the whole time. Yeah. One of these what? I just pinched my finger. It's good.
On our, that's why I didn't think it was supposed to turn in, because we had one of the actual reactions that we had to watch.
Oh. No, I'm not doing that demo right now. I know what you're asking. Ask me that later, okay? Why is that funny? Why is that funny? Is this Freddie Mercury? You know who Freddie Mercury is?
No.
You know who Freddie Mercury is? What band or group? What's the band? Queen. Queen! Thank you. Queen. I'll play you can play. Okay. So, Rich Schindler, I have a combustion reaction for you. What does combustion usually mean? Fire! Thank you. Alright, you're probably gonna have to move. Yeah. Your big heads are okay. Your big heads. Okay. So this is gonna be fun. I'm thinking it's gonna be beautiful, but just can we hit the G slide off? We don't need it. Okay, watch closely. Go to the side. This is her water. Woo! Jeez. That was so loud. Woo! So, yeah, okay. Bring back a little bit there. I don't want to go. Okay. Keep going here. Woo! Rubber handle over there. Sacrifice is certification. There you go. Right. Fine. This one? Yeah. Keep putting out my fire. Okay. So you can hear the pitch. Can you hear the pitch differing? won't work again. If it doesn't work again, shouldn't. Because it's a volatile, it's ethanol on the bottom of this, so it's very, very volatile, right? Thank you, turn my back on. So it's very, very volatile, meaning there's a lot of vapors hanging out in the empty space, right? But once I combust the vapors are no longer there, so I can hold the mag string, it's not going to work once there's more vapors. So, and the green that you saw is boric acid. Boric acid makes a really bright green light whenever it combusts. Okay. So, just waking you up between problems here, okay? So, next one. Example 3 for me, and then you guys are doing yours. Consider. I'm considering. Are you considering this? Consider this, okay? The single replacement reaction between magnesium and copper 1 chloride. Reaction, go. Mg, I heard you. Magnesium and CuCl, because we have copper 1, chlorine 1, crisscross down, 1 and 1. Good. And what's it going to replace? So who replaces who? Huh? Right, the free element magnesium is active, and it replaces copper out of that relationship. Probably because magnesium's cute and copper's not. That's probably what's happening here, okay? Magnesium replaces copper to make what? Magnesium chloride, what's the formula? Cl2, good, because magnesium is a 2+ charge. Don't forget, you're crisscrossing charges every day. Okay, and then you got copper. All right, so balance. Sorry. Okay, copper 2. There we go. Chemistry every day. Okay. All right. I was close to the hood back there for a minute, and it just kind of rubbed off on me. Really? Come on, people. I call that, like, we have mine's west side, and Mr. Ringdale's is east side. Our hoods, they fight. Come on! It's funny. Okay. All right. So it's balanced. What are we starting with? Oh, this is the new one. I have to show you about molarity. Okay. So I'm going to write down the two pieces of information we have. 500 mils of 0.4 molar copper 1 chloride. Molar. What does molar mean again? Oh, don't use my number, my new number, because I made up the 2 molar one. This is now 0.4 molar. So what did the molarity units break down to? 0.4 moles, right, of copper chloride over 1 liter of solution, right? Well, I don't actually have a full liter of solution. I only have the way this is written, molar is moles per liter, always. I can flip this if needed. I'm not going to flip it yet, though, okay? So I'm starting off with milliliters, but I have liters as a conversion factor. What do you think I should do with milliliters first? Convert to liters. How many liters is that? Half a liter, right. There's 1,000 milliliters in 1 liter, yeah? Common knowledge. And then half that, so 0.5. 0.5 liters is what we're starting with of solution. Okay, so now I've got 2 starting points, but these 2 starting points are just going to be multiplied together to get me to moles. So that's why I told you at the very beginning with the whole flow chart thing. So let's actually figure out what we're looking for. What are we looking for? How much copper? So question. Much copper. Much means mass, okay? Grams of copper is what I'm looking for. So how much copper will precipitate out of the solution? So you're going, oh, she means solid. This is solid precipitate. Okay. So the first 2 pieces of information I have to use as a combined effort to get to moles. Basically, I'm doing what I told you to do earlier. This is 0.5 liters times the molarity. When you times the molarity, what cancels? What cancels? Liters of solution, good. Liters and liters cancel. Now we're in moles, and we can go anywhere. We can go to the rainbow, guys. Moles. But I don't want to go to the rainbow. What do I want to go to? Copper. Give me the copper. I know I got to get rid of moles of copper chloride, or copper 1 chloride. I know I got to put moles of copper 1 chloride down here, and I know I have to put number of moles of copper on top, but what are the numbers? What? Both of them are 2? Yeah. You're right. 2 from the copper 1 chloride and 2 from the copper from the BCE. So, you guys saw that, right? You guys got that on your paper. There were 2 moles of copper, 1 chloride, and there were 2 moles of copper. And then, your last and final step is to do what? What's molar mass of copper? Okay, good job. 1 mole of copper. So you'll notice here I have moles of copper, 1 chloride, moles of copper, 1 chloride, go away. Now I'm canceling out the moles of copper here and here, but 1 mole of copper was 63.55 grams of copper. Copper. And the final answer is copper, 12.71 grams of copper. And why did I record 4 sig figs? What did I start off with in the problem? Ooh, I should have only recorded 2. Lies. I'm a liar. Sorry, I'm a liar. There's only 2 sig figs here, so 2 sig figs. So round this to 2 sig figs. 13 grams of copper. There you go. That's your appropriate sig figs. All right, 2 more on this one. But pretty much everyone started off with different givens, so this is good. You guys have a good example of everything. So, question? What? Question, molecules. If I put M-O-L-E apostrophe C, you know that's molecules, yes? Alright, that's molecules, just because I'm getting tired of writing molecules out. Alright, so how many molecules of magnesium are needed if 102.0 grams of copper, 1 chloride are formed? I don't care what the question says. I don't care if it says we're reacting, there's an apocalypse, and the zombies are eating us. I don't care. I pull out the 2 givens, or the unknown in the given, and move on. Okay, so don't get caught up in the words on these types of problems. So what are you starting with? 102.0 grams of copper chloride. Who do you want to get? Or sorry, you don't care about grams. Moles. Give me the moles. 63.55 plus 35.45. 64. 99. Thanks. 99 grams of copper, 1 chloride is equivalent to 1 mole of copper, 1 chloride. Next. Ratio. What's that ratio? Between magnesium and copper, 1 chloride. 1 mole of magnesium, because there was a 1 coefficient for magnesium. And then 2 moles of copper chloride, because I got that from the 2 coefficient for copper, 1 chloride. Alrighty. Oh, so close. Molecules of magnesium. Good. 6.022 times 10 to the 23rd molecules magnesium is equivalent to what? 1 mole magnesium. Right. It's always about that mole. Grams of calcium, copper, 1 chloride. Moles of copper, 1 chloride. Go away. Moles of magnesium. Go away. Stuck with molecules of magnesium. Makes me happy. We're done with this one. You just need to multiply across the top and then divide by the stuff on the bottom. And we're groovy, baby. We are 3.10 times 10 to the 23rd molecules of magnesium. This is my jam. I love doing stoichiometry. I don't know about you guys. It's just, once you get the hang of it, it's just cancel units. It's just repetitive, but it's easy. You got to get past the fact that, or you got to get past the point of just knowing what the conversions are. Josh, I will cut you. When'd you mess with my stuff? I was like, that took me 3 days to get right. 4 days. It's Thursday. I started last week. Okay. Question. Mass of magnesium needed. I really won't cut Josh. Maybe. I don't know. Alright, so what mass of magnesium is needed to react completely with 0.340 moles of copper, 1 chloride? What am I starting with? 0.340 moles of copper, 1 chloride. Next. Mole ratio, which was I know there was a 2 for moles of copper 1 chloride. There was a 1 mole for magnesium. Last step. Loud and proud. Molar mass. 1 mole of magnesium. 24.31 grams of magnesium. 24.31, that is, yes, that is correct, yeah? Yeah. Answer, 4.08 grams of magnesium. So, if you write down your given and you write down your unknown, you will never be lost. You will always be found, okay? You will be good. Moles of copper 1 chloride, moles of magnesium, grams of magnesium, which is what you wanted.
That's not what it comes down to.
Really?
4.13.
Oh, it's because on my paper. Sorry, on mine I only put 24 grams. Apparently, I was being a little bit lazy on the whole periodic table thing. So 4.31, 13. I'm also dyslexic. Okay. So I want you guys to start practicing by yourself. Examples 1 and 2 for sure should be done in class. We got like 40 minutes left, 35 minutes left. If you're doing examples 1 and 2, you can work with a buddy. Please stay on task. Ask me questions. I'm going to pass out papers. You're doing examples 1 and 2 from your student practice paper. The only lab stations, so you can work at those 2 are those 2. The stuff in the middle is my area, just because I got stuff there. So your examples look like nope. Oh, exothermic reactions. Sorry, I forgot another joke. I said them before they were cool. Because they're cool after they're exothermic. Okay, so student practice 1. That's you. I want to see the first 2 examples done. Go. Work together. Get a calculator.
How many pages?
They should be long. Yes. It's under my Google Classroom. So if you go to, you want me to show you how to get on my Google Classroom? Jamie, just Google Classroom. You have to be logged on with your Cabarrus Apps account. Yes, you do separate chlorate. Chlorates break down. Where are your notes for reactions? Decompositions. How do they break down?
Metal chloride
And balance. So Jamie, when you go on my Google Classroom, it'll have like dates and due dates and stuff like this, all just pasted down the page. So Monday the 30th, the Mythbusters research brief is due. So when you click this, it walks you through how to do it. So it says like, make a title. This is a lot of reading, but I explain a lot on how to do it. Okay, so you make a title, you find 3 to 5 reliable sources based on your topic. I gave you the ACS blog link so that you guys have some access to extra articles. And then I gave you some stuff that you can research about to put in your research brief. I know, you should know what you're doing by now. And I said write a 3-paragraph summary. Just 3-paragraph summary. It's like a page, maybe a page, and then a works cited page. And I give you like exactly what to do right here. So you see title, author, you. Your claim, your hypothesis, your research. It's like one page. Monday.